Let's examine function block diagrams together through the microdiagram program. In this video, we'll see physical input-output blocks, logic blocks, and calibration blocks. Let's take a digital input block onto the screen. When we double-click or right-click on the block, a pop-up window for object properties opens, where there are 3 tabs containing parameters, line definitions, and notes related to the block. When we click on the reserved digital input number, we see the digital input number between 0 and 15. The reason for this is that the device selection in the PLC and expansion section is RTU301, which has 16 digital inputs, and you can change the input number from here. For example, let's set the digital input to 10. Underneath each block, the B block number represents the M Modbus address. The Modbus addresses of digital inputs start from address 1000, and the next binary value will be 1001, 1002, 1003, and so on. In this way, we can make our selection. When we double-click in the line definition section, as we mentioned in our previous video about adding line labels, you can add an fault tag by adding a connection tag to transfer the fault output to the block output if you want to use this fault output at multiple points. Additionally, in the Notes section, you can add detailed information about the area or block if you wish. Let's continue. Our next block is the digital output block. When we double-click on the block, the Object Properties pop-up window opens. By the way, let's provide some details. When it is said to add to the log record buffer, when the logger block is active, the relevant blocks are added to the log record buffer. If you want to monitor a value via an LCD screen or web interface, you can change and view the value of the relevant block on the LCD screen or web interface by selecting Monitor or Monitor and Change option. At the same time, block number, connection tags, and other relevant categories also become active as MQTT formats. If there is no monitor, in the Parameters tab, there is a section for dedicated digital input-output numbers. When we check this option, it is seen that 0 to 7, a total of 8 digital output numbers are specified. This indicates that there are 8 digital outputs on the RTU301 series. Our next block is the analog input block. Similarly, in the analog input block, you can select any of the 4 analog inputs. As you can see, the Modbus address is now 6000. Analog blocks, which are float values, start from 6000 and continue with an increment of 2. You can decrement like 6002, 6004, 6006 for the binary values. Word registers start from address 4000, and long registers will start from 8000. Analog output block, since there are 2 analog outputs on the RTU, selections can be made for 0 and 1. If more analog outputs will be used in the project, you can purchase an expansion module, add an expansion module from the projects section, and increase the number of points. Let's quickly make an example. I added an 8-channel analog output module. When checking the block parameters again, it can be seen that this time selections can be made up to 9. As for the relay output, there are 4 relay outputs on the RTU. For the RTD temperature input, according to the PT1000 sensor, there are 0 and 1. If you want to use this block, this feature should be specified at the ordering stage. Our locked blocks are used to handle a fault and maintenance in a field. For example, during maintenance, you may want to keep a digital input information as a constant. In such cases, you can lock the relevant input number and set the lock value from here. Thus, if you want to send a constant value, you can lock it, and after the fault is repaired, you can ensure that the original Additionally, with these blocks, you can also perform scrolling operations on analog input values or analog output values. For example, if you have a 4 mA data, when you set the scrolling value as 2, you can send an additional 2, resulting in a value of 6 mA. Let's continue with the logic blocks. What can be done with logic blocks? Edge gate, NOT gate, logical operations, high gate continuously producing high, low gate continuously producing low, pulse relay, shift block, and special gate block are included. Let's go step by step. First, let's talk about the edge gate. Let's add an edge gate block to the editor screen. We see the inputs and outputs. When we enter it, we can choose how it should perceive the signal. Rising edge, falling edge are 3 different detection types available. From the cycle type section, you can choose to send in one circle cycle or a continuous send. Regarding the usage of the blocks, by the way, you can click on the programming manual from the help section to access detailed information from there as well. Now explain with examples. Let's go step by step by taking a digital input. First, let's explain the difference between rising edge and falling edge for processing. I selected it as a loop and let's check the controls. When I activate digital input 0, it will send an instant pulse for the rising edge, while there will be no change for the falling edge. And when I bring it down from 1 to 0, it will send an instant pulse for the falling edge. The reason for this instantaneous pulse is that a loop time is selected. If we had selected continuous, there would have been a continuous send. Let's continue with rising or falling, which means it will send an instant pulse both when it rises and falls. Let's talk about sending continuous value. To view the difference between rising and falling, both block cycle type is selected as continuous. I showed an example in our previous videos as well. When we connect blocks to the inputs of the block and make the rising or falling or loop or continuous selection from there, the selections made in the block parameter settings no longer matter. The priority always goes to the blocks we connect to the block inputs. Let's quickly show the NOT gate, which, as you know, is our block that turns 0 into 1 and 1 into 0. Let's take another digital input block. Some sensors normally work in a closed state. In this case, if you want the output to be 0, you use the NOT gate. The information coming Now, let's move on to the AND OR gates, or logic blocks. Let's take one AND gate and one OR gate onto the screen. You can connect a register block or a digital output block to their inputs. Let's connect a binary. When I start the simulation, let's activate both blocks. For example, the AND gate produces a 1 at its output only when all the inputs are active. So, when both are active, the output of the AND gate becomes 1. For the OR gate to produce a 1 at its output, it's enough for any one of its inputs to be 1. Let's continue. Stop the simulation again. Similarly, the and not gate, or the and not gate and or gates, take the exact opposite of the current state of the and or gates. We can visualize examples of the XOR gate from the help section with examples. There are also high and low gates. The high gate always produces a 1 output, while the low gate always produces a 0 output. For impulse relay, if you want to set a set reset circuit in a system, you need to use the pulse relay. Let's briefly talk about the block. The block has 3 inputs and 1 output. When you double-click it, there's no need to set any parameter values inside the block. The block output changes position on a rising edge trigger at the TRG block input. When the block output is low, 0, applying a rising edge trigger, logic 1, to the TRG block input causes the block output to transition to high, 1. When the block output is high, 1, applying a rising edge trigger, 1, to the TRG block input causes the block output to transition to low, 0. When the set block input is high, 1, regardless of the position of the TRG block input, the block output is high, 1. When a rising edge trigger is applied to the res block input, the block output always transitions to low, 0. When the res block input is high, 1, even if other inputs Let's watch this situation with the simulation. Our next block is the shift block. The shift block is used for parsing data into its bits and shifting bits left or right. When you shift bits to the right, you add 0 to the left, and when you shift bits to the left, you add 0 to the right. Let's move on to the bit merge block. In the bit merge block, we can view all 8 bits here. The output will be active based on the values coming to these bits, the bit inputs. Let's move on with an example. For example, you have multiple digital input data, and you want to operate different points according Let's visualize it with the simulation. When we activate digital input 2, we see that the outputs are 1. I removed it from the circuit. When I activate digital input 3, we get 2 for 2 to the power of n, 2 to the power of 1 is equal to 2. When I activate digital input 2, it will be 3 because of 2 plus 1. And let's activate the last bit as well. We get 100 We have a custom gate block. This is one of our custom function blocks. You decide what the output will be based on the input values. When we double-click, we see the input values here. You can manage outputs such as making it 1 when 4 is 0 and making it 0 when 3 is 0 and 1 is 1. You can adjust it like this. Let's make an example. For example, when 4 is 1 and the output is 0. Let's visualize the scenario. Let's take a digital input block for this and connect it to the input. Let's start the simulation. When 4 is 0, the output became 1. Because we defined it that way in the custom gate block. Let's also visualize when we want to make its output 0 when 4 is set to 1. When I activate 2, 3, 4, and 5 inputs, we will see that the output is 0. Our next block is calibration blocks. First of all, where are they used? If you have a 4 to 20 mA analog input or a 0 to 10 V input value, and you want to calibrate it with a value, you can easily do it with the point calibration block. Let's start with the slope calibration block. Let's use a word register block to write a value here. The logic is as follows. Multiply the incoming value by this value. That is, you can set the word register value with this unknown value, that is, -1 in the negative direction, +1 in the positive direction, +2, and so on. Let's make an example. Let it take 3 times the value I wrote and add 5. Since it takes 3 times the value of 100 I set, it added 5 directly to its own operation. I set the word register value to 100, and it took 3 times the value of 100 and added 5. This way, you can use the slope calibration block. The point calibration block is a block we use very often. You can view x1, y1, x2, and y2 parameters here. You can enter x1, y1, x2, y2 from inside, or set them from outside. As I said before, the priority is always the values you enter from the outside. Also, if you check the option Trig while active, it calibrates according to the pulse coming to the trigger input. Otherwise, there will be no change in the output even if any value changes. That is, when the trigger is active. Let's continue. Our first value, for example, let's take 4 to 20 mA as a reference. Let's calibrate 4 to 20 mA between 0 and 100. My starting value is 4, and my ending value is 20. In the first point, we calibrated between 0 and 100. For our test, let's take an analog input onto the screen. I connected the analog input to the input. Since I did not activate the trigger while active, there is no need to activate the trigger input. The block will work in this state. Let's start like this. As soon as -25 is displayed, the block expects 4 mA to come. When it's 4 mA, the point calibration block is at position 0, and I'm increasing it up to 20 mA. With each increment, the calibration block changes, and when it reaches 20 mA, the output of the point calibration block becomes 100. If an intermediate value is to come, let's say 17.5, you can get the output as 84.375.